For the time being, assume that this can be done. Now let's go back to our diagram. Which all transistors are on? We already saw N3 and N4 being on. A was previously written as 0, so this 0 goes to the input of this PMOS and P2 turns on. So do you all agree that P2 is on? Great. If P2 is on, node B was pulled at 1 and this one goes at the input of N1 and P1. Because it's a logic 1, N1 will turn on. So from the left hand side, N1 is on. From the right hand side, P2 is on. Along with that, as seen previously, N3 is also on and N4 is also on. So now here, first we will see what's happening on the left hand side. Here, N3 being on and also N1 being on, and we want to write a 1 at node A, I would strongly suggest and bit is at VDD and bit bar is at logic 0. Let's not touch the left hand side of the circuit. Why? For the simple reason I have already sized for my read stability W by L of N1 to be stronger than W by L of N3. So let's not touch the left hand side for the time being. Let's go and investigate the right hand side circuit. Okay, let's quickly see what's going to happen. On the right hand side, I had P2. I had an NMOS transistor which we labeled this as N4. This was my nothing but bit bar line. This was my VDD. You all remember A was initially at 0, which was given as the input to P2, so this was on. This was nothing but my node B, which was initially at 1, initially. Now I want to write a 0 here. N4 was also on because my word line was also equal to VDD. So what's going to happen here is, and remember what was bit bar? Yes, that's true. Bit bar was at 0. So what's going to happen is, see the fun. P2 is on and it is trying to pull node B towards VDD. Do you all agree? P2 is on. It is trying to pull node B towards VDD. Yes or no? Yes. N4 is on and one point of N4 is at ground and the other point is at logic 1. What's going to happen is same, a tank concept, 2 tanks, different levels of water will flow, and if there is a connection through a pipe, water will flow from higher level to lower level till the time both the tanks have water of same levels. So here this guy bit bar is at 0 and B, node B is at 1. So current will flow from higher potential to lower potential. That means B will go down because of N4, and at the same time bit bar is also going in the upper direction. Now what's happening is N4 is taking node B to 0, N4 is taking node to 0, and P2 is keeping node B to logic 1. Both of them are trying to play with node B. If you remember, we discussed that we want to write a 0 at B. Who is taking node B to 0? N4. So who do you think in this battle of fight should win? P2 or N4? That's fantastic, you have got it right. N4 should win, because if N4 wins, then I can write a 0 at node B. And if that happens, you know what has just happened? We'll quickly see. If 0 is given at node B, or if 0 is written at node B, this 0 is connected back. Let's understand where is the 0 connected. We'll understand it in a minute when we draw the 6 transistor SRAM diagram again. So if N4 wins, I can write a 0 at node B. So what do we understand? That W by L, because N4 needs to win, of N4 should be greater than W by L of P2, which is nothing but, as we discussed in the previous clips, that W by L is directly proportional to current ID, and following Ohm's law, V equal to IR, and if voltage is constant, I and R are inversely proportional to each other, which states that W by L is inversely proportional to R. So can I say R of N4 should be less than R of P2? Great. Now let's see what's happening at the right hand side of the circuit after the 0 has been written at B.